Hello everyone, I'm Sharat Ibrahimpur. Today I'll present our work titled Minimum Norm Load Balancing is Almost as Easy as Minimizing Makespan. This is joint work with my advisor Chaitanya Swamy. Let me start with the motivation for this work. A recurring theme in combinatorial optimization is that feasible solutions induce a multidimensional cost vector. Let me illustrate this with three examples. In the spanning tree setting, we have a connected graph with weights on edges. A spanning tree in this graph induces a cost vector whose entries correspond to weights of the edges in the tree. In K clustering, we have a set of endpoints in a metric space that we want to partition into K clusters. The entries of the n-dimensional cost vector consist of the distance of a point to its assigned cluster center. Lastly, in the load balancing setting, we have a set of n jobs that we want to process on m machines. Any assignment of jobs to machines induces a load vector on the machines, but the load on a machine is simply the sum of processing times of jobs assigned to that machine. The goal in these problems is to find a solution that minimizes a certain aggregate of the induced cost vector. Going back to our example, minimizing the sum of costs gives the classical minimum spanning tree problem and the K-median problem. Next, if our aggregation rule is to pick the maximum cost, then we get the bottleneck spanning tree problem, the K-center problem, and the Makespan minimization problem. Let's talk about objective functions and what they model. The two most commonly studied objectives are the min-sum and the min-max objectives. If we are trying to minimize the sum of costs, then it means that we are taking a utilitarian view. Instead, if we are trying to minimize the maximum cost, then it means that we are taking an egalitarian view. That is, we want the worst of agent to not incur too much cost. It's not hard to see that these two objective functions tend to skew solutions in different directions. LP norms are sometimes used to interpolate between these two extremities. A substantial amount of research effort goes into finding approximation algorithms for a particular objective function. Since objective functions are a means to an end, it is natural to ask the following question. Is there a meta algorithm that works for a wide class of objective functions? To this end, Chakrabarty and Swamy considered the class of monotone symmetric norms and gave constant factor approximation algorithms for load balancing and clustering problems arising from such objectives. Let me formalize what I mean by a monotone symmetric norm. Most of you would be familiar with the definition of a norm, so I won't get into it. A norm is monotone if increasing a coordinate does not lead to decrease in the norm. And a norm is symmetric if it is invariant under permutation of its coordinates. In this talk, I'll often use the notation x with a superscript of down arrow. This is shorthand for the vector x with its coordinates sorted in decreasing order. Let me mention two reasons why we should work with such a wide class of objective functions. The first benefit is that we can capture a lot of interesting objectives under one umbrella. For instance, all LP norms are in this family. There's another special subfamily of monotone symmetric norms called topple norms. The topple norm of a vector is simply the sum of its L largest entries. As you can see, topple norms give another natural way of interpolating between the min-max and the min-sum objectives. A well-known mathematical result called the majorization inequality shows why topple norms are considered the building blocks of all monotone symmetric norms. If you have two vectors x and y such that the topple norms of x are bounded by the topple norms of y, then for any monotone symmetric norm f, the f norm of x is at most the f norm of y. The second advantage of working with monotone symmetric norms is the increased modeling power. Observe that a pointwise maximum of monotone symmetric norms is yet another monotone symmetric norm. So an optimization problem with multiple norm budget constraints can be cast as a problem with a single norm minimization objective. A few slides later, I'll show how this idea is used in stochastic load balancing when jobs are Poisson random variables. I'll now formally describe the main problem that we consider in this work. It's called minimum norm load balancing. We have a set of n jobs that need to be processed on exactly one of m unrelated machines. The processing time of a job j on machine I is Pij. We are also given a monotone symmetric norm f, via value oracle. Feasible solutions to this problem can be represented as an assignment function from jobs to machines. On the right, you can see a diagram that shows 8 jobs assigned to 4 machines in a certain fashion. The load on a machine is simply the sum of processing times of jobs that are assigned to it. So each assignment induces an m-dimensional load vector on the machines. Our goal in this problem is to find an assignment that minimizes the F norm of the induced cost vector, of the induced load vector. An important special case of this problem is when machines are identical. In this setting, the processing time of a job does not depend on the machine it is assigned to. Next, let me mention what's known for minimum norm load balancing. I'll first consider the setting when machines are unrelated. Leinster, Schmois, and Tardosh gave the first 2 approximation algorithms for Makespan minimization. That is, the case when F is the infinity norm. Azar and Epstein extended this result to all LP norms. Recently, Chakrabarty and Swamy gave a 38 approximation algorithm for the most general version of min norm load balancing, which they later improved to a 4 approximation algorithm via a very natural convex program. Next, for the identical machine setting, Hodgbaum and Schmois were the first to give a p-task for Makespan minimization. Later, Alon et al. Extended this result to all LP norms. Now I'll mention our contributions to this problem. Our first main result is a 2 plus epsilon approximation for min norm load balancing on unrelated machines. Our second main result is a p-task when machines are identical. Observe that our guarantees essentially match the gold standard for the important special case of Makespan minimization. Min norm load balancing has also been studied in the stochastic setting. Here we have a set of n independent stochastic jobs that need to be processed on exactly one of m unrelated machines. The processing time of a job j on machine I is a non-negative random variable xij, whose distribution is given to us. Like in the deterministic case, we are also given a monotone symmetric norm f. Now, an assignment of jobs to machines induces a random load vector, where the load random variable on a machine is simply the sum of job random variables that are assigned to it. Our goal in stochastic minimum norm load balancing is to find an assignment that minimizes the expected F norm of the induced load vector. A special case of this problem arises when job sizes follow a Poisson distribution. That is, the instance is specified via non-negative real numbers lambda ij, which denote that the processing time of job j on machine I is a Poisson variable with mean lambda ij. Let me mention what's known for stochastic minimum norm load balancing. Constant factor approximations are known for several important cases. Kleinberg et al. Were the first to give an order 1 approximation for stochastic Makespan minimization on identical machines. Gupta et al. Generalized this result to the unrelated machine setting. Subsequently, Molinaro extended the result to all LP norms. Just last year, we settled the case when F is a top L norm, and also the case when jobs are Bernoulli random variables. For the most general case, we gave an order log m over log m approximation. In all these works, the constants are quite large, often in the hundreds of thousands. Goel and Indick considered a further specialization of the problem when jobs are Poisson random variables. Their intention was to give simple approximation algorithms with good approximation guarantees. They gave a 2 approximation for stochastic Makespan minimization on identical machines with Poisson jobs. In the previous iteration of ICAL, Day, Khanna, Lee, and Nikpe gave a p-task for this special case. Now I'll mention our contributions to Poisson minimum norm load balancing. Our main result here is a very simple and beautiful reduction from Poisson minimum norm load balancing to deterministic minimum norm load balancing, where we lose a 1 plus epsilon factor in the reduction. The main feature of our reduction is that it preserves the machine environment. Okay? Combining the above theorem with theorems 1 and 2 on min norm load balancing, we get a 2 plus epsilon approximation for Poisson min norm load balancing on unrelated machines, and a p-task on identical machines. Observe that theorem 4 is a substantial generalization of de Etol's results. In the remaining time, I'll give a high-level overview of two results. First, I'll talk about the reduction from Poisson min-norm load balancing to deterministic min-norm load balancing. Then I'll talk about our 2 plus epsilon approximation for min-norm load balancing. Due to time constraints, I won't cover our result on identical machines. We now focus on stochastic load balancing when jobs are Poisson distributed. Let's start with some preliminaries. It's a well-known fact that a sum of two independent Poisson variables is yet another Poisson variable. So the machine loads that we encounter in Poisson min-norm load balancing are Poisson variables. For an assignment sigma and a machine I, we define the lambda load on I to be the sum of lambda ij's of those jobs that are assigned to machine I. We refer to this vector as the lambda load vector for sigma. With this notation, an assignment sigma induces a random load vector whose ith coordinate is an independent Poisson random variable with mean lambda I. It will also be helpful to define a function g that maps an m-dimensional vector y to the expected f norm of a random vector whose ith coordinate is a Poisson variable with mean yi. Now, let's recall the problem formulation for Poisson min-norm load balancing. With the notation on the previous slide, the objective is to find an assignment sigma that minimizes the g value of the induced lambda load vector. Let sigma star denote an optimal assignment. The key idea in our reduction is a property called shear convexity that the function g has. If you have two vectors x and y, such that the topple norms of x are bounded by the topple norms of y, then g of x is at most g of y. Note that this result looks similar to the majorization inequality. However, I would like to mention that g is not a norm in general. What's the takeaway from the above theorem? If we can find an assignment sigma such that the topple norms of its lambda load vector are bounded by beta times the topple norms of the optimal lambda load vector, then we get an approximation guarantee that depends only on beta and the optimal lambda load vector. In fact, we'll shortly see that this ratio is at most beta. If you focus on the box to the left, you'll notice that these constraints are simply norm budget constraints. Recall from the introduction that we can replace these multiple norm budget constraints with a single norm minimization objective. This is exactly what we do in our reduction. Consider the function h, okay, which maps x to the maximum ratio of the topple norms of x to the topple norms of the optimal lambda load vector. H is a monotone symmetric norm because it's a pointwise maximum of monotone symmetric norms. For simplicity, let's just assume that we know the denominator exactly. Our reduction is strikingly simple and can be explained using only 4 steps. First, consider the deterministic min-norm load balancing instance where job sizes are lambda ij's. And the norm that we want to minimize is h. This instance has optimal value at most 1 because sigma star has h norm 1. Let's use an alpha approximation algorithm on this min-norm load balancing instance to get an assignment sigma whose lambda load vector has h value at most alpha. Using the definition of h, we have that for any L, the topple norm of the lambda load vector is at most alpha times the topple norm of the optimal lambda load vector. It turns out that the function g is subhomogeneous. That is, for any beta larger than 1, g of beta times x is at most beta times g of x. Overall, this gives us an alpha approximate solution for the given Poisson min-norm load balancing instance. We now switch gears and consider deterministic min-norm load balancing on unrelated machines. Recall that our objective is to find an assignment that minimizes the F norm of the induced load vector. The previous best approximation for min-norm load balancing was a 4 approximation by Chakraborty and Swamy, which was obtained via a convex programming approach. Unfortunately, the convex program has an integrality gap of roughly 4. So to obtain a 2 plus epsilon approximation, we need new ideas. We give a stronger linear program for min-norm load balancing. We then use iterative rounding framework to round a fractional solution to this LP. For the rest of this talk, I'll use sigma star to denote an optimal solution and the vector O as a shorthand for the load vector induced by sigma star. We will also fix a small positive constant epsilon that dictates the approximation quality. By majorization inequality, to obtain a 2 plus epsilon approximation, it suffices to obtain an assignment sigma such that the topple norms of the load induced by sigma can be bounded by 2 plus epsilon times the topple norms of the optimal load vector. Before delving into the algorithm, I would like to mention what tools are available to us from prior work. Note that unlike LP norms, topple norms are not separable. So Chakraborty and Swamy work with the following characterization of topple norms, which is in some sense separable and convenient to linearize. For any non-negative scalar theta and a coordinate I, we can bound xi by theta plus the portion of xi that lies above theta. This yields an upper bound on the topple norm as shown in the displayed equation. That is, topple norm of x is at most L times theta plus summation over all coordinates, the max of xi minus theta, comma 0. In fact, this expression is minimized when you pick the Lth largest entry of x, when theta equals the Lth largest entry of x. Next, when we are working with m-dimensional monotone symmetric norms, it suffices to only focus on log m many coordinates. Let pos denote the set of integers from 1 through m that are roughly powers of 1 plus epsilon. Observe that there are roughly log m over epsilon coordinates of this form. An easy simplification of the majorization inequality is that it suffices to only work with L's that are in pos. This can only hurt our approximation quality by a 1 plus epsilon factor. To simplify the exposition of our algorithm, I'll make some additional assumptions. First of all, we'll assume that for every L in pos, we know the Lth largest load in the optimal load vector. We call this quantity TL. We now extend T to an m-dimensional vector by recursively setting TL to be TL minus 1 whenever L is not in pos. It is not hard to argue that this only leads to a 1 plus epsilon loss in approximation. Next, consider the individual job sizes in an optimal solution. We only consider those Pij where I equals sigma star j. For L in pos, suppose that we know the Lth largest individual job size. We'll call this quantity zeta L. We will also assume that we know the first 2 or epsilon cube largest jobs. We call these jobs as large or big. And we'll use tau to denote the size of the smallest job in this list. So it's the smallest large job. Okay. I'll now describe the linear relaxation for min-norm load balancing that we use. I'll use variable Zij to denote the portion of job j that is assigned to machine I. The LP that I'll show is just a feasibility LP. It is used to determine if our guesses of TLs and zeta Ls are correct. We have 4 kinds of constraints in this LP. The first ones just say that Z is a feasible fractional assignment. That is, each job is assigned to exactly one machine. The second set of constraints encode our guesses of large jobs in an optimal solution. If a job J is large, then Zij should be 1 if and only if I equals sigma star j. Also, If any Pij is larger than tau, then the corresponding Zij should be 0. This is to ensure that the fractional solution is consistent with sigma star on big jobs. The third set of constraints impose that the topple norm of the LP load vector should be at most the topple norm of the optimal load vector. Here we use the proxy for topple norms that we saw on the previous slide. Lastly, in the fourth set of constraints, we encode that there should be at most L-1 jobs in the fractional solution that are bigger than zeta L. This is exactly what the optimal integral solution does. I'll briefly mention how the rounding procedure works. Let Z bar denote the fractional solution obtained by the LP that we saw on the previous slide. We start with an auxiliary program that has assignment constraints. Next, for each machine I, we add a constraint to bound the load on machine I by the load prescribed by the fractional solution Z bar. We also include constraints that bound the number of jobs that are larger than zeta L by L-1. By construction, Z bar is feasible for this auxiliary LP. Our goal now is to round Z bar to an integral solution while ensuring that none of the constraints are violated too much. As mentioned before, we use the iterative rounding framework. In particular, our rounding strategy is very similar to the recent work of Lynn Harris et al., where they show how to round a fractional matroid basis solution subject to a few additional matroid independence and knapsack constraints. Without delving into the technicalities, our rounding strategy yields an integral solution Z hat with the following guarantees. First, the load on each machine exceeds the prescribed LP load by at most 1 plus epsilon times the largest job that is processed on that machine. Next, Z hat and sigma star agree on their respective 2 over epsilon cubed large jobs. Lastly, for Ls in pos that are larger than 2 over epsilon cubed, the number of jobs in Z hat that are larger than zeta L is at most L-1 plus epsilon L. The integral solution Z hat is a 2 plus epsilon approximate solution because we can split the load vector induced by Z hat into 2 parts. One of the parts, which we call P, simply consists of the heaviest job on each machine. The other part is everything but the heaviest job. The load vector induced by Z hat can be bounded by the load vector induced by the fractional solution Z bar plus 1 plus epsilon times the vector P. This follows from the displayed equation A. Each of these 2 load vectors have F norm that is bounded by the F norm of an optimal solution. So overall, we get a 2 plus order epsilon approximation. With this, I conclude my talk. Thank you for your interest in our work.